Given two strings, needle and haystack, we need to return the index of the first occurrence of needle in haystack, or return -1 if needle is not a part of haystack. For example, let's say haystack is ABCDEFG and needle is CDE. Then you can see that the first occurrence of CDE in ABCDEFG is here, which starts at index 2, so we would return 2. Now, as a disclaimer, it's actually very easy to do this using built-in libraries and methods. For example, in Python, we could just say return haystack.find needle, and that would work. But that's not going to impress any interviewer. What the question is really asking you is, if you were to implement this find method, how would you do it? So the brute force solution would look something like this. We'd line up the two strings and compare them letter by letter. The first letters, A and C, don't match, so we'd move up the needle one character and compare it with the second letter of the haystack. These don't match either, so we'd move the needle up again, and now we have a match. Since they matched, we now advance to the next letter of the needle, and we have another match. So now let's move up to the last letter, and now we see that we found the location of the needle in the haystack. Now, this approach works, but let me show you the problem with this. So let's use a more complicated example. Again, the top string is the haystack, and the bottom string is the needle. First, we'd compare the first characters of each string, and it's a match. So now let's look at the second characters. It's a match, and the third characters match as well, and so do the fourth. But on the fifth character, we have a mismatch. And because of this, we have to start over and move the needle up one character. And now we have to go all the way back and compare the first character of the needle with the second character of the haystack. And so this is the problem with the brute force solution. We made it all the way up to the fifth character, but once we hit a mismatch, we had to go all the way back to where we started and move up only one character at a time. So next, we'd see that B and A are a mismatch, so we'd move the needle up one. This is another mismatch, and now we've got a match. However, the second characters don't match, so we'd move the needle up again, and now we're finally back to where we left off. I'll stop here, but the point is, that's a lot of wasted computation. In the worst case, for every character in the haystack, we would make it almost to the end of the needle, but hit a mismatch at the very end, and then we'd have to go all the way back and do the same thing again for the next character. In other words, we would have to loop through the needle for every character in the haystack, so this algorithm runs in O of m times n time, if the length of the needle is m and the length of the haystack is n. Now, there's a few algorithms that can optimize this, but the one that I'll be going over is the KMP algorithm. Let me start with a demonstration of how it works. So KMP starts the same way by comparing the first characters, and if there's a match, then we move up, and we'll keep going until we hit a mismatch. At this point, instead of going back to where we started, we ask ourselves, well, since we know that the first four characters matched, out of this substring, are there any letters that appear at both the front and back of the substring? In other words, we are asking, does this substring have a prefix that is also a suffix? In this case, the answer is yes. The letter A appears both at the front and the end of the substring. It is both a prefix and a suffix. And so because we know that the needle starts with the letter A, we can actually skip the next two characters and move up the needle all the way up to here, so that the A's overlap and we can resume our search. Notice that we didn't have to move the arrow back at all, because since we already know that the A's match, we can continue our search from the next character. So now we'd compare A and B, which is a mismatch, so the only thing we can do here is just move the needle up by one character and start again. The A's match again, then the B's, and then the C's, but now we hit another mismatch. So let's ask ourselves again. Out of the portion that did match, do any of the characters at the front overlap with the characters at the back? And this time, we can see that none of them do. So since we know that no prefix overlaps with any suffix, we can actually just skip that entire portion and move the needle all the way up here. Here we have another mismatch, so we'll just move the needle up again. Then we start getting matches again, and we almost make it to the end, but we get a mismatch on the last character. So again, we'll ask, are there any prefixes that are also a suffix? And the answer is yes. This time, AB appears at both the beginning and the end. So again, we'll move up the needle so that the ABs line up. And remember, since we know that those two characters match up, we don't need to move the needle back, and we can just pick up where we left off. Now let's finish this up. The C's match, A's match, B's match, and finally the D's match. And we found the needle in the haystack. Now, since we never had to move the arrow backwards, we only traversed the haystack once. Now, we did have to traverse the needle more than once, but again, since both the arrow and the needle never moved backwards, if the length of the haystack is n, then traversing the needle added no more than n steps. This means, in the worst case, there would be a total of 2n steps, which means that this algorithm runs in O of n time. Now, there's one other question that we haven't answered yet, which is, how will we know how far to move up the needle? To answer that, we need to introduce the concept of the longest proper prefix that is also a suffix, which I'll call LPS from now on. A proper prefix is just like a prefix, but it excludes the entire word itself. So, for example, if the word is ABCAB, then the proper prefixes are A, AB, ABC, and ABCA, but not ABCAB, since that's the entire word. And the suffixes, starting from the back, would be B, AB, CAB, BCAB, and ABCAB. So you can see that the longest proper prefix that is also a suffix is AB, because it appears at both the beginning and the end of the word. So as part of the KMP algorithm, we would first need to find the length of the LPS of every possible prefix of the needle, and store that in an array. So for example, if this was the needle that we were trying to find, then we'd start by looking at just the first letter A. The length of the LPS of the first letter by itself is always 0, because a proper prefix cannot be the entire word. Now let's look at AB. Still no LPS, so it's also 0. And it's the same case with ABC. Now what about ABCA? The letter A is the LPS, so we'd record a 1 here to indicate that the LPS is 1 character long. And finally, looking at the entire word, the LPS is AB, so we'd record a 2 here. Now, during the main algorithm, as we traverse the needle, this array can tell us exactly how many characters overlap at the front and the back of each step of traversing the needle. Now, there's one last thing I need to go over before we go into the code, and that is that we also need an efficient algorithm to create this LPS array as well. So here's how we're going to do it. The length of the LPS of just a single letter is always 0, so we'll start by looking at the first 2 letters, AB, and we'll also create 2 pointers, one at the beginning of the prefix that we're looking at, and one at the end. Then we'll compare the 2 characters. Since they're different, we know that the LPS is still 0. Then we'll compare the third letter with the first letter, and the A's match, so we'll record a 1 here, and move both pointers up to see if we can keep going. The next characters don't match though, so we end our streak and just record a 0, and move the orange pointer back to the beginning to start again. However, it turns out that we don't actually need to move the orange pointer all the way back to the beginning each time, and I'll show you what I mean. So now we'd compare the A's, which match, so we'll record a 1 and move both pointers. B's match, so we'll write 2 and move both up again. A's match again, so now we're at 3. Now we have a mismatch, but we shouldn't just blindly move the orange pointer back to the beginning. Instead, notice that the part of the word that we scanned with the orange pointer and the part of the word that we scanned with the purple pointer are the same. So now let's ask, what is the length of the LPS of just ABA? And we can find that answer by looking one index before the orange pointer, which shows that we already calculated that as 1. In other words, this tells us that the first and last A's overlap, so we can just move the orange pointer to the second character and begin the comparisons from there. Here, we see that the B's match, and since we already know that 1 character matched from before, we'd write 2 here. We'll be using something similar to this strategy for the main algorithm as well. If the length of the needle is m, then this part ends up being O of m. So that makes the entire algorithm O of m plus n. But since we know that m is less than n, it's also correct to say that the algorithm is just O of n. Now we're ready to look at the code and do this in Python. Let's say the string at the top is the haystack, and the string at the bottom is the needle. And I've also indicated the indices of each character below them. The first thing we need to do is create the LPS array, and we'll initialize it to 0 for each character in the needle. Since the LPS is the same length as the array, these indices here are going to represent the indices for both the needle and the LPS array. We'll then create a variable called pre, which is going to be used to figure out the LPS of each prefix in the needle. So like we did in the example earlier, we'll enter a loop and start the I variable at the second character. If the characters don't match, this inner while loop will move the pre variable back to the correct spot until it reaches index 0. But here, since pre is already 0, this is false, so we'll skip this. Next, we check if the 2 characters at our 2 pointers are equal. Here, A does not equal B, so there are no matches and we just move on. Next, we can see that the characters match, so we'll move up pre to index 1 and assign a value of 1 at the I index. So the length of the LPS of ABA is 1. Looking at the next letter, we have another match. So again, we'll move up pre to index 2 and assign a value of 2 here. For the last letter, we have a mismatch. So to figure out how far to move back the pre variable, like we mentioned earlier, we'll look at the LPS value that's right before it, which is 0. This tells us that AB has no LPS, so we'll go back to the beginning and move pre back to index 0. We do one final check with A and C, and since they don't match, the LPS value stays at 0. And now we're done with the pre-processing and we're ready to go into the main algorithm. We're going to use 2 pointers here, N to traverse the needle and H to traverse the haystack. Now let's start comparing characters using a similar strategy to what we did above. This part will move N backwards whenever there's a mismatch. This part will increment N if there's a match. And if we make it to the end of the entire needle, then we found it, and we can just return the starting index. So here, the first letters are a match, so we can just increment N, check our ending condition, and compare the next letter. The B's are also a match, so let's increment both pointers again. Now we've hit a mismatch, so let's look at the LPS value that corresponds to the part that did match. We see a value of 0, which means that AB has no LPS, so we can just move N all the way back to index 0, like this. By doing this, you can see we skip the second letter in the haystack, and we can resume our search at the third letter. Next, N is 0, so this is false, and the A doesn't match up with the C either. We also haven't reached the end yet, so there's nothing we can do but to move up H. Notice that I didn't actually move up N, it's still at index 0. Next, the A's match up, so we'll move up N. Then the B's match up, so we'll move up both pointers up again, and then we have another match. And after moving up both pointers again, we find yet another match. However, the last character is a mismatch, so again, let's look at the LPS of ABAB, which is 2. This means that we know that the first 2 characters will overlap with the last 2 characters, so we'll move N back to index 2. In other words, we resume our search at the third character. Now we can see that the third characters do match, so let's move up both pointers, and now the B's match. And finally, on our last iteration, the C's match as well. So since the last letters matched, we're going to increment N to 5, which now makes it equal to the length of the needle. But now let's think about which index we need to return. H points to the end of the needle in the haystack, but we want the starting index, so we're going to do H minus N. However, since N is actually one index past the last character in the needle, that would actually put us one character too far behind. So that's why the correct index to return is H minus N plus 1, which is 9 minus 5 plus 1, which correctly gives us index 5, and we're done. The last thing to note is that if we traverse the entire haystack but we never find the needle, then we would never make it to this line, and the for loop would end, and we would just return -1, which signals that the needle was not found in the haystack.